So what is a sink? I'll show you what a sink is. So this video, we're going to talk about sinks. And of course, the whole point of a sink is no matter where the water is, it's going to flow into the sink. It's flowing towards that equilibrium point. I pulled this video. I did not anticipate the creepy little fingers popping in at the end of the video, but we're here to talk about sinks. I gotta see it again. It's just like oh gosh, that brings me joy. Hopefully it brings you joy. We can find joy in mathematics. So an equilibrium point is a sink if lambda 1 and lambda 2 are both the same sign, and specifically, are they both negative or both positive? Saddles, which we also had a picture, was a saddle point was when they were both different signs. A sink, what do you think? Well, why don't you think about our phase lines? Okay. Getting unhinged right now. Right? A sink is when we flowed towards this. And remember, did this behavior happen along straight line solutions for negative or positive eigenvalues? That's right. It was for negative eigenvalues. So if they are both negative, we have a sink. So let's talk a little bit about that and do an example. Consider dy dt is some matrix times y. We did an A matrix, a B matrix, and now it's time for our C matrix. All right, and we're going to do a bit of a boring matrix to start. All right, and I'm going to give you a general solution. You can pause the video and get the general solution if you want, but I'll just give it to you. Y of t is equal to k1 e to the negative t times the eigenvector 0, 1 plus k2 e to the negative 4t times the eigenvector 0, 1. And I want you to notice a couple things. First off, I want you to ask yourself, what are the eigenvectors and what are the eigenvalues? And hopefully you can identify those pretty quickly. Right? The first eigenvector is just negative 1. It's the coefficient up here. Not a coincidence. We have a diagonal matrix, which we'll learn about in linear algebra, not here. And then the second eigenvalue is negative 4. Again, not surprising. And then they also have corresponding eigenvectors, 1, 0, and 0, 1. So we know a lot of things about this. Let us create our very own phase portrait, because we can do that now. All right. We're going to take this to a new page, do a nice phase portrait by hand. I think we'll use bigger boxes this time. So we go to our graph paper, we make sure to label our axes. We're going to draw our straight line solutions. We're going to use lambda to talk about which direction everything is. This is the XY plane. Very important to remember to label your axes because they're different in differential equations. All right, so we have one eigenvector. Oh, these are boring straight line solutions, right? They're just the axes. Here, I'll use a thinner thing so we can actually see this maybe. Oh, this is, no, that was a terrible mistake. So here's one straight line solution. Here's the other straight line solution. And V1 is x is 1, y is 0. So this is our V1. And the sign's negative. The sign's negative on both of them, right? Both of these solutions will go towards our equilibrium point. They both have negative eigenvalues. Now, what we should expect is no matter where we start, we should kind of, go to the equilibrium. Now, you don't know whether we go to the equilibrium like this or whether we go to the equilibrium like this. You don't really know that yet. I actually do know that, and we'll talk about why we know that soon. In fact, actually, why don't we do it right now? Why don't we do it right now? What's the relationship between our x component and our y component here? Right? What is x of t? X of t is the x coordinates. That is just k1 e to the negative t. What is our y coordinate? That's just k2 e to the negative 4t. Now notice, watch this. Y is really just some constant times x to the fourth. Is that not correct? Raise the x thing to the fourth power, and you get y differing by some constant. So y is always some constant times x to the fourth. We have a little cortex right here. We have a little cortex. That's what our face portrait looks like. You don't need to necessarily know that's true, but it is a cool piece of analysis we can do. Look at the relationship between x and y. And you might say, Jason, how is this possible? Isn't this supposed to be a source? Well, don't be tricked, right? This is one solution. This is another solution, right? The curve looks like a quartic, but those are two different solutions on the left and the right. So we're not crossing an equilibrium solution. That would violate uniqueness. And this is a very nice differential equation, so definitely we have uniqueness. Here's a third solution. Here's a fourth solution. We could draw more solutions, but they're all going to look like quartics because of this specific relationship between x and y. All right, let's draw this with a computer. Should we see the creepy hand again? No, that'd be crazy. All right, again, we draw this, we use this face plotter. You can use both. I'll give you both. All the links to all the plotters that we use are on the top of Canvas. All right, so if we go up here, dx dt is going to equal negative x, and dy dt is equal to negative 4 times y. We graph the phase plane, and oh, what do we see here? Ah, look at that. Yeah, we see a bunch of, again, each solution, right, is only part. Right? We're not actually graphing quartic functions, but they do look like that when you plot mirrored solutions. And of course, we do have a straight line solution when y equals 0, and another straight line solution when x is 0. We see the eigenvector here and here. And again, everything, let's look back at the direction field. Every arrow is eventually going to point to 0. Because that's our stable equilibrium. I haven't told you what stable means yet. Sorry. That's our sink. And then there's the creepy hand coming in over here. All right, and again, this also may seem like they're touching. They're not. They don't even ever hit 0. None of these curves ever touch 0. They get asymptotically close to 0, which we can see with a general solution, right? E to the negative t is never touching 0. It's getting very close, but it's never touching it. Similarly, one of these solutions is getting very close to the origin, but they're never actually hitting the origin. Okay, things start moving very slowly when you go around here. That's one of the nice things about this phase plane plotter is, again, it has color coding for how time affects things. So things are taking a really long time to move around there. Okay, that's pretty much it. That's the whole video on sinks. Once we learned about saddles, that's kind of the most complicated things. We have another video talking about, okay, what can more complicated sinks look like? And we will also introduce some new things, get more practice on old things. But again, you've already kind of done the hard stuff. We got more videos with more fun stuff later. What do you think I'm going to do for a source? I don't even know. I haven't pulled up the video for a source, but we'll have something for a source. Bye-bye.